All right, we made it to the last notes of Unit 3. This one's called Molecular Polarity and Intermolecular Forces. In these notes, we're going to expand on our knowledge of polarity and figure out if entire molecules are polar or nonpolar. So in the last notes, we talked about how certain bonds can be polar or nonpolar, and in these notes, we're going to figure out how whole molecules can be either polar or nonpolar. We're going to start these notes with a review from last notes in the first question, which is, how can we tell if a bond will be polar, nonpolar, or ionic? All right, we can tell what type of bond it's going to be by looking at the difference in electronegativity between the two atoms that make up the bond. So remember that a nonpolar covalent bond is going to have a electronegativity of less than 0.5, so from 0 to 0.49. And remember, in nonpolar covalent, those electrons are shared equally, right? Now, in a polar covalent, okay, the electronegativity is between 0.5 and 2.1. And so in a polar covalent bond, these electrons are shared unequally. So there's one of the electrons that has a stronger pull on the electrons than the others. The one that has a stronger pull has a partially negative charge, and the one that's kind of losing that tug-of-war battle is a partially positive charge. All right, and then last but not least, we've got our ionic bond, which is if you do the difference in electronegativity, so if you take the two atoms that are in the bond and you subtract the electronegativities values for each, and you get a number greater than 2.1, then it's what we call an ionic bond. And remember, in ionic bonds, the electrons are transferred. Okay, so from one atom to the other, from the metal to the non-metal. So we get full charges here, not partial, but full charges. So the metal atom in this case is potassium. He becomes a positive 1 charge, and the chlorine gains or gets that potassium electron and becomes a negative 1 charge. All right, so that is kind of review of what we talked about last time. Now we're going to apply this to figure out how we can tell if an entire molecule will be polar or nonpolar. All right, so to answer the second question of how we can tell if an entire molecule will be polar or nonpolar, we must look at the shape and polarity of all the bonds in the molecule. So that's why we had to learn about shape. That's why we had to learn about the bond polarity between two atoms, because we're going to put these two things together to figure out if an entire molecule will be polar or nonpolar. First, we're going to take a look at the easy one. If you check out the difference in electronegativities of all of the bonds in a molecule, and you find that they are all nonpolar, okay, then the entire molecule is nonpolar, right? Because if nobody's winning the tug of war, then everybody's sharing equally. So the entire molecule will be nonpolar. So let's take a look at an example. All right, let's take a look at this example of methane, or CH4. All right, so if we do the electronegativity values for carbon, okay, carbon is 2.55, and hydrogen is 2.10. And so if we take the difference there, the difference is 0.45. Okay, so we can see that all of the bonds in this molecule are basically being shared pretty fairly. So we're going to call all of the bonds nonpolar. Because all of the bonds are nonpolar, the entire molecule is nonpolar. Another example is fluorine gas, F2. So in fluorine gas, it's just two fluorines hooked up together, right? So let's see, 5, 6, and 1, 2, 3, 4, 5, 6, 7. Okay, so we've got a something looks like this. So we have two fluorines hooked up together. If we take a look at their difference in electronegativities, it's going to be 0, right? Because 3.98 for one fluorine minus 3.98 for the other fluorine is a big fat 0. So fluorine is going to share his electrons very fairly between the two atoms, and so therefore it's going to be non-polar. So both of these guys, okay, because their difference in electronegativities of all of the bonds is non-polar, both these guys are what we call non-polar molecules. All right, so that was the easy one. Now we're going to take a look at if we do the electronegativity differences and some bonds in the molecule end up being polar, okay, some or all of the bonds end up being polar, then this is where it gets a little more complicated because you actually have to look at the shape of the molecule and the overall pull of electrons, okay, the overall direction of the electrons being pulled. So let's take a look at it at an example. All right, so let's take a look at carbon dioxide. Carbon dioxide is carbon in the middle with two oxygens bonded, double bonded, on either side of that carbon. So if we take a look at the electronegativity differences between oxygen and carbon, oxygen is 3.44, right? Carbon is 2.55. So we get a difference of 0.89, which means that the bond between carbon and oxygen is polar. So if we actually take a look and draw out the polarity of it, oxygen, right, it's got a higher electronegativity, so it's pulling harder. So we've got a pull on the electrons towards both of the oxygens. So the oxygens will be slightly negative, right, and carbon will be slightly positive. Now, the shape of carbon dioxide is linear. It's a straight across line. And if we take a look at the overall direction of the pull of electrons, we are pulling equally in opposite directions, right? We've got one oxygen over here pulling with a strength of 3.44, and we have another oxygen 180 degrees from it pulling in that opposite direction of 3.44. So nobody's winning the tug of war. Remember, if nobody wins the tug of war, it's a non-polar bond and a non-polar molecule. So since we have equal pull towards both sides, okay, equal pull towards both sides, this molecule is non-polar. All right, so carbon dioxide, even though the bonds in carbon dioxide are polar bonds, it is a non-polar molecule because we've got equal and opposite pull in both directions from those from the oxygen atoms on the carbon. All right, we're going to take a look at another example, okay, to see how this works. So our next example is HCF3. Okay, so this molecule, which will look like this. Carbon will be in the middle since he makes the most number of bonds, and he's going to have 4 bonds, 1 to an H, and 3 to 3 fluorines. Okay, so he'll look like this. Now, if we take a look at the difference in electronegativities for both bond types, we're going to take a look at carbon and hydrogen bond, and then also the carbon and fluorine bond. We can see here that the carbon-hydrogen bond is a non-polar bond. Okay, so nobody's winning the tug of war there between the sharing of those electrons. They're shared pretty equally between the carbon and the hydrogen. However, between fluorine and carbon, there's a little fight going on here. So the difference in electronegativity between fluorine and carbon is 1.43. So that means that the carbon-fluorine bond is a polar bond, right? So where each of the fluorine atoms is, winning that tug of war, all right? So we've got the fluorines being slightly negative, and in this case, the carbon is slightly positive. So now we have to take a look at, since some of these bonds are polar, we have to take a look at the overall shape and direction of electron pull. All right, so pulling from left to right, we've got equal and opposite pull in both of these directions. Okay, so That's not going to help us. That means, in that sense, going from left to right, it's nonpolar. However, if we take a look at the up and down directions, we have more of a pull this way towards fluorine and not really any pull at all up here towards hydrogen, okay, because they're sharing fairly. So we have most of the electrons in this molecule being, around this part, okay, not really towards the top. So because we have unequal pull in at least one direction here, we are going to have a polar molecule. All right, so there we go. Unequal pull of electrons in at least one direction is going to make it a polar molecule. All right, so by this point in this unit and probably in chemistry, you're asking, why the heck do I need to know this? Well, here's a couple of, applications to this, molecular shape and polarity and stuff like that. So the third question here is, did you know that molecular polarity is actually related to smell? All right, here it is. We can smell polar molecules. It's the polar ones that we can smell, but not the nonpolar molecules. So we cannot smell nonpolar molecules unless they are really big. Okay, so, and big enough to kind of bombard through, to get to our smell receptors in our nose. So it's whenever you're smelling something, it must be a polar molecule. Now, for some of you smart people, you might be thinking, well, water's polar. How come we can't smell water? And it's likely due to that our bodies are made of mostly water, and so it's probably habituation. Like everything of us is made of water, so it wouldn't be really a good idea for us to be smelling water all the time, because then we would be smelling like, I don't know, everything. So we can smell polar molecules except water. And we cannot smell most non-polar molecules. So there's a little trivia for today. All right, our second application is the fact that water and oil don't mix. And you may have, experienced this firsthand when cooking, or even if I've got a good example in the hood of my classroom. I've got a little water bottle of water and oil that aren't mixing. So why don't water and oil mix? Well, it all has to do with being polar and nonpolar molecules. And so now you actually know the science or the chemistry behind why water and oil don't mix. So let's take a look. All right, so here it is. It's called the like dissolves like rule, meaning that so like dissolves like, meaning that polar molecules will only dissolve in other polar molecules. So like, they have to be alike in order to dissolve in themselves. And then nonpolar molecules will only dissolve in other nonpolar molecules. So again, it's the like dissolves like. So water is a polar molecule and oil is a nonpolar molecule. So that's why they can't dissolve in each other. All right, so water, again, polar molecule, cannot dissolve in oil, which is a nonpolar molecule. And other words that describe this, if you remember back in biology when you're talking about cells, hydrophilic and hydrophobic, okay, are the same type of things. So molecules that are hydrophilic are polar. Molecules that are hydrophobic, okay, are nonpolar molecules. So that's a little biology tie for you. All right, let's take a look at our very last question of these notes, which is, how are individual molecules held together in a liquid or a solid form? All right, so our last concept of this unit is, how are individual molecules held together in a liquid or a solid form? So let's take a look and review what we've been talking about this entire unit, which is basically called chemical bonding. We've been talking about intramolecular forces. Intramolecular forces are between atoms in a molecule. Okay, so whenever we're talking about intra, it's like internal. So between atoms is intramolecular forces. That's stuff like ionic bonds, covalent bonds, and metallic bonds. Those are intramolecular forces. They occur between atoms in a molecule. Now, this last thing that we're going to talk about is intermolecular forces. So these are forces that hold molecules together. Okay, so they're between molecules, not atoms. Okay, so intermolecular forces are between whole molecules rather than little atoms that make up the molecule. So in this case, we are actually going to just focus on a couple of them. From this list, we are just going to do hydrogen bonding, dipole-dipole, and London dispersion. So let's take a look at these three. All right, so like I said in the last slide, individual molecules are held together by what are called intermolecular forces. Okay, another word for them are van der Waals forces. Okay, a guy named van der Waals came up with this idea, so we can also call it by his name, van der Waals forces. In either case, it's the force between molecules that are holding each other, together. So we're not talking about individual atoms now. We're not talking about bonds. Okay, so these guys are not bonds between atoms. Okay, they are forces that are holding molecules together in a liquid or solid form. All right, there are three types of intermolecular forces that we're going to talk about. The first type is called London dispersion. This is going to hold nonpolar molecules together. Okay, so London dispersion holds nonpolar molecules together. It's the weakest force of them all. And it's why nonpolar molecules are going to evaporate very easily. Another characteristic of these is that they're very volatile, meaning they evaporate easily. So tomorrow in the little lab kind of demo thing that we're going to do, you'll see that the nonpolar molecules are going to evaporate super easy because, again, their molecules are held together by this weak force called London dispersion. Our second one we're going to talk about is called dipole-dipole. This type of intermolecular force holds polar molecules together. Okay, so this is much stronger because, remember, polar molecules will have slight charges on their opposite ends. And a molecule with a slight negative charge on one end will be attracting a molecule with the slight positive charge on its end. And so we're going to get attraction of oppositely charged poles to each other, and that's going to hold polar molecules in solution, in a liquid or solid form. All right, and the very last one that we're going to discuss is called a hydrogen bond. And I put bond in quotations because, remember, it is not a real bond, okay? It's not two atoms coming together to make a bond like we've been talking about, all right? It's just a very, 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 very strong intermolecular force. In fact, it's the strongest one that holds polar molecules together, and it's called a hydrogen bond because it must have a hydrogen in it and another highly electronegative atom like oxygen, nitrogen, or fluorine. Okay, so if your molecule has a hydrogen and either an O, N, or F, okay, then the molecules are going to be held together by this hydrogen bond intermolecular force. Okay, but again, it's not a real bond, a chemical bond. It's just a intermolecular force that is very strong, that it's almost, kind of, the strength of a bond. But in any case, those are the three intermolecular forces, and tomorrow we'll be doing our last activity in lab to reinforce this molecular polarity and intermolecular force ideas. All right, we'll see you tomorrow.